Hi, my name is Mark Hastings and I'm an apps engineer at Cypress Semiconductor. During this video I will introduce you to the PSoC3 and PSoC5 analog routing structure. It is not required to totally understand the analog routing structure, but as your projects get more complex, it will help to achieve maximum performance and the best resource utilization. The analog diagram referenced in this video can be found in the PSoC3 and PSoC5 datasheets in the Technical Reference Manual. Although at first glance the diagram looks like a complicated rat's nest of wires, you will find after a brief study it really isn't that complex. Around the outside you will find all the possible pins for the largest members of the PSoC3 and 5 devices. The smaller parts contain a subset of these pins. In the center are the analog blocks. Everything in between is a routing matrix consisting of analog buses and switches to interconnect the GPIOs and the analog blocks. There are a total of 26 analog buses and numerous dedicated routes between certain blocks to the GPIO pins. I like to view this diagram as divided into 4 quadrants. The upper left quadrant contains ports 4 and port 0. These two ports are connected to the analog global buses AGL 7 through 4. These global buses are routed to the left-hand side of the analog blocks in the middle. Notice that each of these globals are connected to most of the analog block inputs and outputs. Notice the red and white circles. They depict switches between signals. The red switches symbolize low resistive switches with an on resistance of about 200 ohms. The white switches are smaller and have an on resistance of about 870 ohms. The amount and mixture of switches provide a good compromise between a full cross-point switch and keeping the cost and area and route capacitance to a minimum. The other 3 quadrants are similar to the first. The upper right quadrant has one full port, port 3. It connects to analog globals, analog global right 7 through 4. The lower right quadrant contains ports 1 and port 5, which are connected to analog global buses right 0 through 3. The final quadrant at the lower left contains ports 1 and port 6, which are connected to the analog global left buses 0 through 3. All ports are connected to their corresponding analog globals in the same way. Notice the pattern. The ports in the lower quadrants are connected to the analog globals in the pattern 0, 1, 2, 3, 0, 1, 2, 3. The ports in the upper quadrants are connected in a similar pattern of 4, 5, 6, 7, 4, 5, 6, 7. Notice that in both cases, each global is shared by 2 pins on each port in that quadrant. Also, all ports are connected to at least one other global bus called the AMUX bus. There are 2 AMUX buses, one on the left and one on the right. These 2 buses may be connected together at one point. When these 2 buses are connected with this switch, it is possible to interconnect all GPIO pins on a single bus. For example, you would be able to scan all 56 GPIO pins with the ADC. Also notice the switches that connect the left and right analog globals. In this case, analog global left 3 through 0 and analog global right 3 through 0. These switches allow signals on the right to be connected to components on the left, such as the Delta Sigma ADC, which only has inputs on the left side. Of course, signals may be routed from the left to the right as well. The same is true for the upper globals, analog global left 7 through 4 and analog globals right 7 through 4. There are another 8 additional analog buses called the A bus left 0 through 3 and A bus right 0 through 3. These buses are used to make inter-block connections between the analog blocks. This saves the valuable analog global buses I just mentioned for routes between analog blocks and GPIO pins. Notice that these buses can also be interconnected between the left and right side of the analog blocks. I have showed you the main bus structure of the PSoC3 and 5. Some blocks have dedicated connections between an analog block and a dedicated GPIO pin. One of the most important of these connections are between the op-amps and the associated GPIO pins. The op-amps have dedicated routes between the inputs and outputs to a corresponding GPIO pin. Notice the dedicated switches between the op-amp inputs and the GPIOs. It is recommended that you select these pins when using an op-amp. You will not use up the analog globals that way. Notice there is no switch between the op-amp output and the dedicated pin. If the op-amp is turned on, it drives that pin, always. When the op-amp is turned off, it will not affect any signal at that pin. The same is true on the right-hand side for the op-amps that connect to port 3. There are a few other dedicated routes as well. When using the IDACs in the high current range, 2 mA, routing through the normal analog matrix may create excessive voltage drop due to switch and trace resistance. Because of this, there is a dedicated pin that may be used for each IDAC. The output for IDAC 0 has a dedicated route to P06, IDAC 2 to P07. On the right-hand side, we have a similar arrangement. Although these dedicated routes are meant for the 2 mA high current range, it is a good idea to use them anytime you can, since they save the precious analog globals for other routes. There are other connections that I haven't covered, but what I have talked about are by far the most important for most designs. So do yourself a favor, take a few minutes to understand this diagram. I keep a couple small printed copies to mark up and have a large 3-foot by 4-foot hanging up on the wall across from my office. Thanks for taking the time to watch this video. I hope this will help you understand the PSoC3 and PSoC5 routing structure.